But maybe let me ask a couple of questions first before I go into this. Who has used a supercomputer like Pitstein or Uqueen or the system in Barcelona or anything like that before? Please raise your hand. Okay. Excellent. Who has programmed for any of these machines before in parallel? Very good. All right. Who has ever done the profiling? Okay, maybe I won't blow you out of the water then. All right, good. High-performance computing is actually all about bottlenecks. Because high-performance computing is computing at the limit. All right, what kind of limits? The first limit most people think of is the CPU. Most people are thinking flops, operations per second, not necessarily floating point, that they can do. But this is only one of the limits that we typically encounter. And more, it's not the most common one either. Increasingly, memory is actually becoming the limit. CPUs have gotten faster and faster, memory has not. That's why we are actually dealing with lots of hierarchies in memory. And the people at Intel have been telling me for years, you know, flops are free. Every memory transfer costs you. Well, maybe if you're dealing with lots of data, not even memory is your bottleneck, but I/O. So how do I get my data on or off a disk? Let's start with the CPU. As I said, this is the limit most people think of, and Olaf already said we're using Eureka or Jurica, whatever you prefer. Eureka is actually a fairly normal cluster, except that it has some different partitions. Some have GPUs, most of them don't. Some nodes have a lot of memory. Most of them are average in memory, but they all actually have the same CPU. Each core on Eureka runs at about 2.5 gigahertz. Fairly typical speed for a CPU these days. This is a Haswell architecture. So we have 256-bit wide vector units, or SIMD units. Each of these SIMD units can perform 2 fused multiply add operations per cycle, which gets us a theoretical peak performance per core at the nominal frequency of 40 gigaflops. Actually, this already is somewhat cheating because, well, for the Xeon processors, once you start using the AVX units, the frequency actually goes down. So not even theoretically can we reach this per core. Yet this is what's usually given as peak performance. Well, each processor actually has 12 cores, which gives us 480 gigaflops per socket, or per processor, per CPU. And each node has 2 CPUs. So for a peak performance of the CPU-only nodes of 960. Why don't I see that one? That's annoying. Okay, 960 gigaflops per second. All right, that's quite a bit per node. The main memory bandwidth is actually too slow to feed these CPUs at the speed that they can produce and consume data. So we're dealing with a cache hierarchy on these processors, going from top to bottom, further and further away from the CPU, and becoming slower. Slower in both latency, So how many cycles does it take to actually get to the CPU, and bandwidth, although it doesn't quite, yeah. So the fastest caches are the L1 cache. The L1 cache often runs at speed, so at the frequency of the CPU, but it's small. Actually, there are two caches. There's also an instruction cache. Here I just talk about the data cache. It can read and write data almost at the same time. The next hierarchy is the L2 cache, and that's what we usually actually optimize for. Because the L1 cache is so small, this is really just a data buffer for the CPU to kind of serve as a register overflow. The L2 cache has a reasonable size. You can fit a small molecular dynamics simulation already completely in L2 cache and work out of L2 cache. L3 then is the largest cache. It is shared between the cores, but it's also the slowest. Well, so we have 30 megabyte of cache already on the CPU. Of course, we have way more than that in main memory, but the main memory bandwidth is only about 60 gigabytes per socket. All 12 cores share a main memory bandwidth of 60 gigabytes per second. And usually this number changes minimally as you add cores. So if we now have processors with 24 cores, they still only have 60, maybe 80 gigabyte per second of memory bandwidth. So everything that you need to get from main memory is really expensive. Let's look at this in a little more detail. Let's look at just a simple operation. I mentioned on the slide earlier a fused multiply add. Does anybody, who knows what a fused multiply add is? Okay, the numbers are getting smaller. Good. No, kidding. A fused multiply add operation is a multiplication and an addition that is done in one operation. So this is exactly what it does. It does C equals C plus A times B. All right. Now, this operation reads, I assume double precision numbers here, 8 bytes, reads 3 double precision numbers and writes 1. All right, that's 24 bytes to read and 8 bytes to write. And for now, I'll ignore all caches. All right, I said I have 60 gigabytes per second in main memory bandwidth. So I have 60 gigabytes divided by 24 bytes per operation reading gives me a peak speed of 2.5 giga operations per second. One operation here is a multiply add, which is usually counted as 2 floating point operations. So my peak performance is 5 gigaflop per second. 5 gigaflops per second. Do you remember what the peak performance of the socket was? 480. So this simple operation, one of the core routines of computing, among other things, the matrix multiplication, which happens in many solver operations, this simple operation is memory bound. Badly memory bound. Now, this simple operation is also the core of what makes up the LINPACK. Who has heard of the LINPACK before? I hope you have. The LINPACK is the benchmark that is used to rank the supercomputers in the world. So Pitt Stein is actually one of the fastest. It's the fastest in Europe right now, and that is in ranking by LinPack performance. LinPack solves a system of linear equations, and the core routine there is matrix-matrix multiplication, and the core routine of matrix-matrix multiplication is this multiply add. So this is the core routine of what ranks supercomputers, so of course the vendors are not stuck at those 5 gigaflops per second, but they use caches to avoid that. All right, let's look at a matrix multiplication. Who knows what a matrix-matrix multiplication is? Okay, good enough. We'll come back to it a couple of times. So here is a simple implementation of a matrix-matrix multiplication. And basically what I do, I have for each element, I take one row, each element of one row, and multiply it with the corresponding element of a column. So basically going like this. And then I add them all up. And I can express that like this. I have 3 loops. This goes over the indices of the result matrix. This does this inner loop. And you see this is a multiply add. All right. Let's take 2 small matrices. A and B, just random numbers. If I ran the code that I just showed you, it would take me about 8.36 seconds to do this calculation. This is significantly slower than 5 gigaflops. You'll later calculate it. So here, each matrix-matrix multiplication with these 3 loops, and you'll have time to look at the notebooks later, performs 2 times n cubed operations. Divided by 8.36 seconds gives me 0.004 gigaflops. That's why they tell us Python is slow and can't be used for supercomputers. Thank you, that was the end of the course. Luckily, it's not. One way to get faster is Numba, and we'll show you more about Numba later. Don't worry about the details right now. Numba, in short, does a compilation of your Python code into machine code using this simple JIT operator. So we take exactly the same function as before and compile it. All right, 30.6 milliseconds. That sounds much better. And it is. We achieve 1.148 gigaflops per second. Quite impressive speed up, huh? But still much lower even than our memory bandwidth limit that we would get. That's because data is actually not fetched 1 byte at a time, but a cache line at a time. So we actually have to reorganize our code. A NumPy ND array, and about those we'll... Actually, how many of you are familiar with NumPy? Ah, good. So we can probably go fast through the NumPy notebook later. We'll see. An ND array in NumPy uses C order, which means we go row by row, basically. But the code that I had did not. I can use almost the same code, but switching the K and the J index and make this actually much better. Now, here in the Cij, I'm going along the fast direction along the row. This actually is constant in this inner loop. And this too goes along the fast direction of the row. Now, from a pure programming point of view, this shouldn't matter. Actually, we get the same result, and we want to. For the computer, this makes a big difference. When it can go along the memory, it can actually, so a cache line contains multiple bytes. Depends on the exact architecture, let's say 64 bytes. So every time we get any data from memory, we actually don't just get 1 double precision numbers, we get 8. If we now go to a random other location and grabbed 8 bytes, then we would cut our maximum bandwidth by a factor of actually 64. We catch 8 bytes, but we load 64, so by 1/8. Doing this, we basically use the entire cache line. So we fetch memory once and then use it. And let's see if this makes the code faster. Yes, we are down to 3 milliseconds and 11 gigaflops. This is, by the way, all in one core. There's no parallelization here, and it wouldn't matter. 11 gigaflops, that's actually more than I would have expected from my simple estimate. And that's because our matrices are actually so small, they do get cached. So I'm not pulling from main memory all the time. Let's make this a little bigger. That is pretty close. So 5 gigaflops was what we expected, and we can actually get that just by using the simple JIT compiler and swapping two indices. Because then we are basically doing what the computer wants us to do and get the bytes or get the data in the right order. Now, again, I said this is something that is optimized by the vendors, at least any vendor that wants to sell supercomputers, because this is the core routine used for the LinPack and thus for rating the supercomputers. And each vendor provides their own library of these matrix multiplications, and many other routines given in a set of BLAS routines, linear algebra routines. And NumPy can be linked to those. On Eureka, NumPy is linked against the MKL, the math kernel library. These numbers I actually did on my laptop. So here it's linked against OpenBLAS, and of course the maximum is a little smaller than on Eureka. My laptop isn't that fast. But with an optimized NumPy routine, you can achieve much more. And you'll later see on Eureka what you get for your results. Now, using libraries is usually good. If you have an optimized library, you should use it. You shouldn't write your code for something where there are well-tested, optimized libraries, because you're just most likely to introduce additional bugs. Of course, this is not always true, but most of the time. This competition between memory and flops is often presented as the ROOFLINE model. Who's heard of the ROOFLINE model before? All right. The idea here is basically I have on the x-axis how many bytes, how many flops I perform per byte that I loaded. So our routine was doing 2 floating point operations, and it was loading 24 bytes. So that would be 1/12 in this metric, flops per byte. So we are somewhere down here. And these curves here have 2 lines. This is the sloping part, which is basically going along the memory bandwidth, just linearly, right? If I can load at max 60 gigabytes per second, then here I would, if I have 1 flop per byte, then I would have exactly 60 gigaflops. If I have half flop per byte, then I'm here at 30 gigaflops. So here in this range, I'm memory bound. No matter what I do here, as long as I use less than 8 flops per byte, roughly, I'm memory bound. 8 flops per byte is already quite a bit. That's quite a bit of computation, because one double precision number already has 8 bytes. So per double precision number that I load, I have to perform 64 operations. If we were stuck just with main memory, I think we would be dead in the water, because we would always be memory bandwidth limited. Luckily, we have more than one memory. So here I added the L2 cache. Now the L2 cache, it's somewhere between half a flop per up to a flop per byte, where you're memory limited, and above that you're actually compute limited, compute bound. Just for comparison, I also added some more limits here. So this would be the limit of a single core without vectorization. So that's not a lot. It's basic, yeah. Without vectorization and also without a multiply add operation. That's the 2.5 basically. Here is the single core peak performance. That was about 40 gigaflop per second. That is now with full vectorization and a multiply add. This is the socket peak. And this is really the relevant one, because for the second socket, again, we have another 60 gigabytes of memory per second memory bandwidth. All right, so we went through the different cache levels. We talked about memory bound and compute bound. But what if I have to load the data from disk? In Jülich, we use the IBM Global Parallel File System. Here we are using Lustre, but in terms of peak performance, there isn't that much of a difference. And we can load about roughly 100 gigabytes per second from disk. We actually can't do that on a single node because it's not connected with that much bandwidth to the storage. But we can access the storage from a job with about 100 gigabytes per second. So we are talking about the same order of magnitude here as the main memory. So if we do it right and do parallel I/O, actually disk bound is not really worse than memory bound, except that I skipped here the second measure that we need, latency. Latency is the time from requesting the data until you received it and actually have it at the processor. That, of course, is much better with the main memory than it is with the disk. If you drive a truck here full of disks to Milano, that is still a decent bandwidth. The latency is horrible. So each node is actually only connected with 1.25 gigabytes per second. So you have to use quite a few nodes to get the main bandwidth. All right. You will not get any slides from us. because the slides were basically all made from the notebooks. So once you have the notebooks, you have all the material that we present here and quite a bit more. Who has used Jupyter notebooks or IPython notebooks before? All right.